Hello everyone. This time we'll be talking about graphical models again, especially focusing on performing map inference on chains as well as trees. So we'll have a typical situation of having a number of sites n, and for each of these sites we have some measurements x, and we want to estimate some world state w. Now if our number n is very large, we're going to have to exploit the conditional independence between our variables. Otherwise, we'll be trying to estimate a large number of w's and looking at the context of all the other w's. But our situation, especially here where we're dealing with chains, is intentionally simplified. We're going to have only sparse relationships between certain sets of w's. So in a chain model, every site, is only connected to one preceding and one subsequent variable. In tree models, we'll see that's a little bit more generalized. So the assumption is that w's are discrete, and the assumption is that our x's can be continuous or discrete, and we have these associations that one observation x is associated with each w, and the x's are independent of each other. So we're going to take this generative approach that the nth observation x is somehow conditioned on the associated w. There are a number of interesting applications for this kind of model where you have a chain, and I highly recommend seeing Thad Starner's work where he was trying to interpret sign language in video and treating the signs as they were gestured by the person as a chain of observations, where we were trying to understand the meaning behind them. There are lots of other examples, not just American Sign Language, but also with various kinds of contour tracking and stereo estimation, and we'll come back to the applications later on in this lecture. Now, we'd introduced the idea of a hidden Markov model previously, such as this one, where you have a chain of w's, and for each w, it's generating a collection of pixels, some observation, some measurement x. Now when we look at the joint probability of all our x's and our w's, we see that this is this massive product over all of the data likelihoods, so probabilities of x given the associated w, times the product of all of the blue directed edges here, where you have conditional probabilities of a given w state conditioned on the previous w state. So you've got the red directed edges and the blue directed edges. The first one is measuring the compatibility of the world state against the measurement. The second one can be looked at as kind of a prior in terms of saying how compatible are different world states. Now in the undirected version, it's actually remarkably similar. You still have terms that represent the compatibility of the world and some measurement, and you have the pairwise term that's looking at the compatibility of different world states. Now, again, these are just potential functions in this case. We could also turn it around and treat these as Gibbs distributions and talk about the costs instead of the potentials for these pairwise terms, for the red edges or the blue edges in this graphical model. But either way, we're still going to need this partition function out front, the 1 over z, to turn the results of these products of functions that could take on any kind of values into actual probabilities. Now, a quick note about that is that whether it's a directed or undirected graphical model, we still have to have a probability distribution on the left-hand side. So when we're dealing with the undirected case, we need that z, that capital Z, to take into account normalizing of both the data likelihood terms and the world state compatibility terms. And so you'll see here that there's a difference between the z sub n's and the z prime sub n's. One is used to normalize the measurement terms, right? That's this first one, and one's used to normalize the world state compatibility terms. But once you work out what the lowercase z's are supposed to be, z and z prime, you can then compute what the capital Z is supposed to be. Just a simple product. Now, coming back to our sign language example, we can say that our likelihood term is going to be this normal distribution on x. So we're saying that the probability of seeing a given measurement x sub n, given that the world is in some state k, where the person is making some specific sign with their hands, is going to be a normal distribution on x with some mean and covariance. The interpretation here is that the person is not going to gesture the particular concept in the same way every time. They move their hand a little bit, they might be wearing a different t-shirt, but roughly there's going to be some mean observation, some mu that represents the average way that this symbol is represented, and some covariance that tells us how different, how varied it might be from person to person, or every time the person gestures that same phrase. Now, the world state compatibility is our prior, essentially, looking at the conditional probability of Wn, given Wn minus 1 is in some particular state. This is going to be a categorical distribution. And so you can think of this as typically as a two-dimensional matrix, which is going to say, what's the probability of moving from some world state W to some world state Wn plus 1. So you can think of this as, in this case, kind of a language model. What's the probability that I might say a particular word followed by some other particular word when we list the comprehensive set of words that I might use in my language. Now we're ready to start doing map inference for the chain model. We'll see in a moment after this that the tree model is actually remarkably similar, and so it'll just be a straightforward extension. Now, in our directed graphical model, we've already said that this is going to be, the joint probability is going to be factorized as a product of probabilities for the data likelihood and the world state compatibilities. When we go to do inference, we care about finding the maximum a posteriori version of all of the W's at the same time, so jointly. And that means when we substitute in our normal distribution from the previous slide and the categorical distribution from the previous slide, we can treat this as a maximization of the posterior, which then ends up being a minimization of the negative log posterior. When we substitute in, we'll have this minimization will be these two sums. And now we're going to repeat that equation, next slide, and we can actually take a general view of this to say that the first term is often referred to as a unary term. It's unary in that it only looks at a specific site, and it's looking at the compatibility between x and the respective w at that same site. And the other term is the pairwise term because it's looking at two sites. It's looking at Wn and Wn minus 1. Because we've moved to log space, these are now sums instead of products. And so we can think of this unary term and this pairwise term as these things that can get added together. And this will be handy when we start performing inference. The short answer is that we're going to use dynamic programming to find the maximum a posteriori inferred solution for our graphical models that are lined up as chains. So we're going to divide this rather large optimization problem into submodular bits and solve for each one of them. And by solving the individual pieces of the smaller problems, subproblems, we're going to find the optimal overall solution. Okay, so we're going to take this graphical model, which has a nice visual representation, and we're going to abuse it a little bit to reshape it to make it look like dynamic programming, also known as the Viterbi algorithm. Now keep in mind that we have unary costs and pairwise costs. We're going to keep the representation that the pairwise costs go from left to right, but we're going to kind of hide the unary costs, saying that for every site we know that there's a unary cost associated with assigning different labels to W1, all conditioned on the likelihood term of how well does that given W1 explain the X1 that we observed. So let's get started. Here we're seeing for every column of bullets, these are bullets now, not nodes in a graphical model. For every column of bullets, that represents a site. So in this first column, we're seeing W1, and it can take a set of discrete different values. W1 might equal 1, or it could equal 2, 3, 4, or 5. And what we're seeing here is U1 represents the unary cost of assigning W1 to the value 1 based on X1 that was observed. So X1 doesn't change, but the compatibility of X1 with each of the possible discrete labels, 1, 2, 3, 4, or 5, is kind of represented here as these sequential bullets, K1 through K5. Now it just so happens that in this chain from left to right, W1 as W2 and 3 and 4 and 5 and 6, they all have the same number of possible states. In other words, the number of discrete choices for each random variable in this case happens to be 5. But you could actually imagine a chain where some have more and some have fewer discrete values k that they can take. For simplicity, let's just assume that they all have the same number. Now, we also are representing our pairwise terms. Now, in a moment, we're going to work our way through the graph from left to right and then trace our way backwards to find a unique solution that is the maximum a posteriori combination of world states for this combination of unary and pairwise terms. The thing to note here is that this kind of picture, this illustration of the world states gives us the opportunity to represent any combination of W1 through W6. So for example, if we end up choosing that W1 should take a value of 2, W2 should take a value of 4, and so on, we could come up with some configuration that is the joint combination of W1, 2, 3, 4, 5, and 6, each of them selecting their favorite, their best overall value, but by looking at all of the pairwise relationships as well. And every other combination is also possible, and we're trying to select the best one among them. So let's look at this in a specific example. Here we are given some information up front. In the for each site, we are told what the unary cost is of assigning W1, for example, to take on the value of 1. It's a cost of 2.0. This is represented as cost, so smaller numbers are better. For assigning W1 a label 2, it's only going to cost you 0.8, and so on all the way down the line from 1 to 5. So we've been given this information. In the case of sign language, this was our normal distribution saying that this was the compatibility between X1 and each of the possible values of W1. Now the pairwise terms have also been given to us. Maybe they've been learned offline, but somehow an oracle has told us that there's a pairwise cost of 2 neighboring world states. And we can look at any one of these nodes here. So we'll start with the one in the upper left here. So you've got W1 for any one of its values. We'll start with the top one, for example. It has a certain compatibility or incompatibility with W2. So to put W1, give it a value of 1, and to give W2 a value of 1 actually costs us nothing. This pairwise cost function is saying if you aren't changing the label So you stay with the same label, giving 1, 1, 1 across, or giving 3, 3, 3 across, for example, then you're going to incur repeatedly pairwise costs of 0. But if you want to change from a particular label, a discrete label 1, to a discrete label 2 in the neighbor, you're going to pay a fixed penalty of 2.0. And for simplicity of this illustration, we've also specified that the pairwise cost between a label and anything greater than plus or minus 1 is infinite. So while we could imagine that there is an edge that goes from here down to here, that would be infinitely costly, and so it's never going to be selected as a possible candidate. So this way we've got the information given to us for our unary costs and our pairwise costs, and now we're ready to get started. So we start off by looking at that first column, W1, and for each of these circles we're going to fill in what is the unary cost of reaching that point. We only have to fill in the unary cost because there was no other cost of getting here. So in this case, we just copy in the unary costs, 2.0, 0.8, and so on. Now we're going to work our way to the right. So we're going to go to W2, and for any one of these nodes, we're going to, for the first one, for example, for k equals 1, we're going to look at the possible ways of getting here from W1. In other words, conditioned on W1, what are the costs that we would incur? What's the minimum cost that we would incur to reach this version of W2? And we can see that we could either pay a cost of 2.0 plus 0. Remember, these are additive, the unary and the pairwise cost. 2.0 plus 0, or we could pay a 0.8 plus 2.0. So that's 2.8 versus 2.0. I know which one I would rather pay. I'd rather pay the smaller cost. 2.0 plus 0 is a cost of 2.0. But to actually get here, remember, I have to pay both that initial pairwise cost, the initial unary cost, this pairwise cost, and this unary cost. And that's what I'm going to write in there. So, in fact, this is what we see, right? Route 1 adds up to 3.1. Route 2, that was coming from here, here, and here, right? That adds up to 3.9. So we prefer the cheaper one, and so we're going to write in 3.1 here and record the fact that we got there by just going directly across. So indeed, we just kept this one arrow, and we've done that same thing for each of our circles in turn, recording what was the cheaper path of getting here. And in this case, for instance, you see that for W2, both these states, whether we end up choosing k equals 2 or k equals 3, they both like it when W1 equals k equals 2. Okay, now we're always keeping the minimum because there'd be no reason to pay the higher cost. So in this way, we've solved these little submodular problems. We've figured out what is the cheapest way of getting from one node W to another node W, from one site to the next site, while taking into account both unary costs of W1 and the unary costs at W2, and all the different pairwise costs along the way. And now we're going to repeat that same process going from W2 to W3. And so we have a general rule, in fact, that you're always going to be choosing to write down your pairwise cost, right? It's going to be where you take the unary cost, which is fixed for a given node, plus the minimum path of getting there, the minimum L, which looks at the previous node and looks at the pairwise costs of getting from the previous node to this version of the current node. So repeating that process, we can fill in W2, keep going, W3, 4, 5, and 6. And now we see what the total cost is. So we're looking now at this last column, we see what the total costs are of reaching the different values of W6. In other words, we could reach W6, where W6 takes the first categorical label, or maybe it's better if it takes the fourth categorical label, and in fact it is, right? This is the lowest cost we could have. So if we're trying to find the maximum a posteriori solution, the highest probability solution, in this case we're using costs, so we want the lowest cost solution, and that corresponds to 17.4. Now, if we select that W6 takes a value of 4, this one that I've put a square on, that also tells us that the previous node, W5, should take a value of k equals 5. And if you take that one, you have to take the associated predecessor, which would be a k equals 4, and so on. So we can work our way backwards, right, from the final column to determine that this is the optimal combination of world states. So this is going to be a value of 2, 3, 3, 4, 5, and 4. So we have our solution, our discrete assignments for each of the W's, W1 through W6, which all together take into account both the unary costs and the pairwise costs. We have a solution to our map inference problem for a chain. Now we're ready to do the same thing for trees, and it's actually remarkably similar. We're actually going to be a little bit more organized, and you'll see how to keep your data organized whether you're doing chains or trees. So imagine that we have this graphical model, which is very similar to a chain, except that now we have W5, which is getting inputs from both W2 and W4. The factorization of it is across the bottom, and again you see we're mostly dealing with these pairs, right? Either nodes that have no parents, pairwise terms, except this one W5, which is conditioned on two inputs, W2 and W4. So in this case, we're going to be looking at the probability of W5 given W2 and W4, which means we're going to have to look at essentially a ternary or a three-way connection, figuring out, well, W5 might have some affinity to try to explain the observed X5, but it's going to have to weigh itself and maybe make a compromise between what its compatibility with different states of W2 and different states of W4. All right, so here we go when we try to generalize this term. The terms from last time, we're still going to have unary terms, we're still going to have pairwise terms, but we're also going to have this ternary term, which looks at three world states at once. Obviously, you can have trees which have more than three, and they keep getting more expensive to solve. So this is what our worked example looks like. For that same graphical model, we still have W1 through 6, but our W5 now has all these incoming edges because any given version of W5 has to consider that the paths that get you here, both from W4 and from W2. So that's why you see these multiple incoming edges. All right, so let's get started. To organize ourselves, we're going to keep track of our pairwise costs with these simple matrices. We didn't illustrate them when we had chains. At the time, it was just a single matrix for every pairwise relationship, but now we need kind of a stack of these. And so the way to interpret this is we're looking at the ternary term for node 5, for W5, and we're looking at what it would take for W5 to take the discrete value 1 or discrete value 2, and so on. So this whole matrix, this first one in the upper left, is looking at this first bullet here. What would it take for W5 to take on the discrete value 1? Well, it has to look at two of its inputs. It's conditioned on W2 and W4. So if W2 is in state 1, so that's up here, and W4 is in state 1, so that's up here, so that would be this edge and this edge coming in. we see that the ternary cost there is 0.4. So someone has given this to us, right? We've learned it in the previous step. Some oracle has told us that. So we know what the ternary cost is of that combination of labeling 1, 1, and 1 for W5. And we have all the other ones illustrated as well. Lots of them are infinity, so we don't see any edges. And we see that some of them might be quite cheap, right? So here you have 0, 0, for example. And we repeat this, so we have this same kind of matrix 4 times, 1 for each of the possible discrete values of W5. So we remember we had the same thing, we just didn't show it when we were doing chains, where we just had a single matrix representing the possible values of the incoming, so the predecessor node, the Wn minus 1, and maybe on the columns, and Wn for the rows. So we're going to do the same process as before. We start on the left, we work our way across. Obviously, you can do W1 and W3 sequentially because they're not dependent on each other. But you definitely have to have W2 worked out, have worked out all these values, and W4 worked out before you can start saying anything about W5. And it's the same procedure as we described before. You look at any discrete value, potential value of W5, you look at its predecessors in W2 and W1, you figure out what the cheapest path is of getting here. Okay, you fill that in. You can complete the tree by going all the way to the far right, figuring out which is the cheapest of the total costs, and then working your way backwards and saying, aha, for W5 to take a value of 2 implies that we had to get here by taking simultaneously this branch from W2 and this branch from W4. And so we have our overall solution for the tree. Now we're going to skip big sections of this chapter for efficiency. And it pains me that we're going to miss out on the forward-backward algorithm, on max marginals for chains, and factor graphs especially. But it's material that you can read in the book if you find you need it. And especially belief propagation is something that would take a longer time to work through, and I encourage you to do it on your own time, but I won't hold you responsible for it in this class. Instead, we're just going to proceed to models with loops and focus on the need for something better than or the Viterbi algorithm, than dynamic programming, to deal with loop situations, and that'll set up our thinking for the next chapter. So let me skip ahead to models with loops now, and please remember, for belief propagation and factor graphs, you'll want to revisit the slides and the sections of the book that I'm skipping. We come to models with loops. So let's imagine that we can't always make our graphical model representation be a chain or a tree. Sometimes it might look like something like this. So on the left, we see that there is a loop between W2, 4, and 5. And had we done factor graphs and belief propagation, you would see that actually you can make a three-way factor. That's this thing here, right, which connects those three nodes, and as a result, this factor graph is actually in the shape of a tree. But missing out for now on factor graphs, we can think of other situations where even using factor graphs wouldn't save us. So frequently we look at images, and images have pixels laid out in this kind of grid fashion. So whether you're looking at directed edges or undirected edges, you have these large numbers of variables which have relationships between their, I think of it as their north, south, east, and west neighbors, in addition, of course, to their data likelihood for that given site. Now, with a situation like this, you see that this isn't naturally a chain or a tree. So what can we do about it? Well, we could try using dynamic programming as we did previously. So we initialize on the left, work our way across, figure out what the lowest cost was, and then repeat the same process to make sure we go through the other node. But then if you see what would happen if we did that, we would walk all the way across to the far right and maybe get lucky and land and conclude that this particular state for W4 is the best for both branches. But then when you trace back, going backwards, you might find that for W1, you now have to make a hard decision to either choose k equals 2 or k equals 4, and one of them is going to be unsatisfactory for the other branch. In other words, we can't agree on the value of W1 in this case. So dynamic programming isn't going to work for these kinds of situations where we have a loop, so we might have some ideas for alternatives. One approach would be to prune the edges. So what was initially this highly connected graph on the left, right? We could imagine that now we take away the loops, and on the right we just have these directed edges where you have branches and the path never loops back on itself. So we've lost some of our dependencies between variables. W3 no longer has this edge to W6, but because it's connected through a bunch of other neighbors, we might get away with it in that we've lost a little bit of the information sharing that was happening, a little of the regularization that was happening between W3 and W6. There's still some present in a kind of second and third order way. Another approach would be to combine variables. So imagine that you have a binary variable W1, maybe W2 and W3 are also binary. So now instead you could imagine as having this combined W1, 2, 3, having 8 possible discrete states, and that would capture sort of all the combinations of 0, 0, 0, 0, 0, 1, etc., down to 1, 1, 1. And so we've made a single node here, this mega node, right? And it now looks like a chain. Of course, each of these mega nodes has a larger number of discrete variables than we did if we just had 0 or 1 at each of the originally occurring nodes. So this is actually completely valid, and it allows us to perform map inference using our dynamic programming that we've already learned. It's not always possible, of course, because you might end up creating mega nodes that have far too many combinations, and this list might grow to be intractably long. So some other approaches, we skipped over loopy belief propagation, but that's an excellent way of doing it and highly recommended. We did mention sampling approaches, although we find that sampling is easiest for directed models because then you can use ancestral sampling. Otherwise, you're having to do Gibbs sampling, which is certainly possible, but can be quite slow when you have a large number of variables. And then there are some other approaches like tree-weighted message passing, and we will in fact talk about graph cuts in the next chapter because it's such a powerful technique specifically designed for situations with loops and discrete labels. Now, a few words about possible applications now that we know how to do map inference for chains and trees. We've already mentioned gesture tracking, where you have a camera. In this case, there's this camera looking down through the baseball cap, looking down at the person's hands. And so here we're trying to estimate what is this person's sign language trying to tell us, and we model it as a hidden Markov model, i.e. a chain of world states connected to each other using these pairwise directed edges, and each world state is associated with an independent observation X. Now, for stereo vision, we also would want to do this kind of map inference. And the argument here is that we would like to do some kind of regularization. In other words, without regularization, we could look at estimating the depth for a pixel, for every pixel in the image, by just estimating the depth of that one point, ignoring its neighbors, Or we could try to take into account the depths being computed for all the neighbors to help us come up with a better overall estimate. And I'll illustrate what I mean here in just a second. So first, let's set up what does it mean to do stereo. In this case, we have the same scene being imaged by camera 1 and camera 2. They're side by side from each other, so they're basically looking at the same scene. But for any given XY location, if you look at the same coordinate on the left and on the right, it actually is a different part of the scene being projected to that coordinate, that XY pixel coordinate, because the scene looks slightly different for your left eye and your right eye. Now, this is an opportunity where we're going to compute some kind of matching to figure out the triangulation between the points in the scene and these two cameras. In other words, if I kind of picture it here in the margin, you might have a camera that's looking at some kind of scene. You have another camera looking at some kind of scene. And while you initially don't know how far away a given pixel is, how far away the surface is imaged by a given pixel, if you could figure out which of the pixels in this camera, all of these are rays coming out of the pixels of this camera, which one of them corresponds to that point, you'd be able to triangulate it and figure out what is the depth of that point. Now, depth is this distance from the camera. But the inverse of depth is the disparity. So disparity is referring to how much of a shift is there when you look at maybe a given point in one camera and the corresponding point in the other camera. How much did it move left or right between the two cameras? The idea is you can think of you can illustrate this for yourself by thinking of looking out the window of a train. Objects will move across your visual field quickly or slowly depending on the distance. Your train is traveling at a given speed, but objects that are nearby are going to travel very quickly because the disparity is very high. The distance is small, therefore the inverse of that, the distance is very small, so the disparity is very high. These objects whiz by through your in front of your window very quickly, whereas objects that are very far away, they will still be moving, but their disparity will change very, very slowly. Therefore, their depth is very large. And so what we're essentially doing is boiling down stereo, estimation of depth, or its inverse, disparity, as being a matching problem. We wish we could find the same thing that we saw, this same part of the geometry, the scene, the appearance of it that we saw at some location in image 1. We want to figure out where did it appear in image 2. Because we know we've just moved our camera horizontally, we know in this case that we just have to do the search along a given scan line. And if the object has a very distinct look, like some kind of corner, then that's going to be really easy. But for regions of the scene where maybe the texture is quite uniform, then it's going to be very hard to say that we have matched some point here against a very concrete version of that point in the left image. There's nothing particular about the appearance of those points that tells us, oh yes, that's definitely a match. And this is where the regularization that's coming in from our chain model might be able to help us. In this case, we're seeing the ground truth disparity on the right telling us what the disparities should be if we ever computed them successfully. Now, we're going to set up our problem by saying that we have a normal distribution on X that's telling us what is the likelihood that for a given world state, and world state here means discrete levels of disparity, for a given disparity, what is the probability of observing that patch of pixels at a given location m, n? And so we're modeling that as a Gaussian. This normal distribution on X at m, n is going to look at the appearance of that patch in the other image, shifted and we're going to have some fixed noise model that says, okay, objects that should look the same from camera 1 to camera 2, subject to some variations. And in fact, that can be quite complicated because shiny objects will change appearance drastically when you look at them from two different angles. But for this and for many stereo applications, most researchers will frequently just assume that the object's appearance stays constant. So it's the constant appearance assumption. Now, if we look at a nice distinct point like this, this one tagged with a red square in image 1, and we go looking for it in image 2, we know, as mentioned, that it's going to be just along a certain scan line in image 2. So we're going to move to each of these discrete locations. So each of these corresponds to a particular discrete value that we might choose as the disparity for the red square pixel from image 1. If we could find that perfectly, if we knew which of the discrete values of disparity we should choose, this one or this one or this one, and of course you should be able to figure out that it's probably supposed to be this one here, then we would know that those points match, and therefore that is the disparity. And so in this case, you can look at the red, green, and blue channels, and you could compare under our Gaussian assumption how similar are the patches at different disparities. So here we have different disparities, right, corresponding to the different disparities in image 2, and we see that there's this nice set of peaks right around here, which are telling us, yes, in fact, that triangle, the peak of that triangle is matching pretty well to the peak of the triangle in image 2. And these other values, these other disparities here and here, they are all quite bad. So they don't seem to be a good match. If we were just trusting the unary terms only and had no pairwise terms, we would probably favor assigning a disparity somewhere in this circled region. So somewhere in this range of disparities seems to be a good explanation. Now, if we look at a different pixel, so we looked at now at this green one here, marked with the green square, it's actually some shade of purple, and when we go looking for it on its respective scan line in image 2, we see that, well, things are a little more complicated. It seems to be a good match for disparities that are negative or quite positive or disparities of 0. All of these versions of different shifts or disparities seem to come up with the same color purple. And so when we look at the quality of that match, we see that in fact it's quite instead of being peaky like it was for the previous example, it's quite spread out, and we see maybe there are different peaks and different troughs, and it's hard to say that any one of these disparities is better than any other. So this is a case where we might want the pixel underneath the green square to be influenced by its neighbors, to say, well, I'm going to assign for you a disparity that's not too inconsistent with your unary terms, as we saw here, but that maybe is influenced by the disparity that we're going to choose for each of your neighbors, because maybe one of your neighbors has a more distinct pattern, more distinct appearance, and in fact we might find that's the case here. At some point there will be this transition from purple to blue, and that might be quite distinct, and we'll be able to match that better. Now, if we proceed, right, we can see what it looks like if we compute and illustrate our disparities, first just treating every pixel as independent. So here we're saying that we're looking at the joint probability of all the W's, but we're just modeling them as completely statistically independent W's and just choosing for each one its world state based on the likelihood of just that site. We're just looking at the unary terms, the compatibility between different disparities for a given pixel, and the appearance, purely the appearance at the disparities for that site in the other image. Now, next thing we can do is what we've just explained. We can treat this as a chain model. So every row of the image is its own chain. These chains don't know anything about each other, so we're not looking north or south in our image, just purely horizontally as a single scan line, right? So now that's a very beefy scan line, overly wide, but we're looking at that scan line and regularizing that way. And you should see that this overall result looks a little bit better than the maximum likelihood one, which does not take into account this prior, which says I would like to choose disparities for every pixel that are in agreement with my neighbor's disparities. The result looks better. You can still see some streaks here because where there was this boundary between the purple and the blue, the regularizer, this notion of let's keep the disparity constant until we get some sort of evidence to the contrary, means that we end up with these streaks because there was a textureless region. And in fact, it's still true that stereo algorithms really suffer in areas that have little texture, right? Where there's uniform colors, it's hard to say anything specific in terms of matching and triangulation. Now we can actually go one further, and instead of modeling each row independently as its own chain, we can model this graph as a tree, which we kind of mentioned earlier as a possibility. So we've cut a lot of edges to keep this from having loops, and you see now there are still artifacts, but overall the result is even closer to the ground truth than previously. This this results in these artifacts that are a little bit different. Instead of having streaks, they're sort of these chunks are either missing or expanded, and part of the explanation there is of course that our tree has large sort of clusters of edges coming out of certain nodes, and other nodes have just been trimmed to kind of be dangling at the end of the tree, and so that's why there's sort of the artifacts are varied throughout the image, whereas the streaks were all pretty consistent. We mentioned pictorial structures where you might want to find different landmarks on a person's body. In this case, you might want to find landmarks on a person's face. Naturally, it would be very easy to make an eye detector, but if you just made an eyeball detector or an eye detector, you might find that the corner of this eye right here actually fires very well and thinks it's detected the corner of an eye here. At the same time, it would fire very well over here in the corner of the other eye. But if you want to know the difference between the left eye and the right eye, you might enjoy the fact that you might have in parallel run a nose detector and a lip detector, and these are all helping each other to disambiguate where they are in the image. In this case, we've had to discretize the space, so the offset of one of these boxes is some discrete integer value, and the number of possible sites is going to be capped so that we don't have too many discrete values for a given world state for corner of left eye. But we can always update that as we go, and if we had to, we could iterate. But for any given iteration, we know we're getting the optimal map inferred value for each of these W's, something that's consistent for saying, yes, this is overall a good layout of a person's face. Naturally, we'd have to learn the parameters for this, so we'd have to learn a likelihood function, so the parameters of our likelihood function for the appearance of an eye or a nose or a mouth. And we would also want to learn the pairwise costs to say, well, I would expect that a nose is going to be sort of south of the eyes, maybe southeast of one eye and southwest of another eye, and certain distances are allowed and other distances are too big. And so all that information would be collected, and you'd learn that from a bunch of labeled data where you'd already labeled the corners and the layouts of these faces. So the same approach we've already described could be applied for human body tracking. The number of degrees of freedom as it increases might make things a little slower to converge, and so corners can be cut. And so the Held-Schwalben-Huttenlocher paper here, it was quite an important contribution in its time. Now there are new algorithms which do their regularization sort of earlier, a little bit upstream, rather than waiting until the final steps to do this regularization. But both are perfectly valid options. And finally, kind of alluded to earlier, this kind of iterative version. So here we have a loop, and even though we're not supposed to work with loops, we're going to pretend that we're dealing with a chain. We're going to do that by breaking the loop in a certain location and saying, I'm going to pin one node here, I'm going to pin a separate node here, we're going to pretend there is no edge between them, and I'm going to optimize all of the variables with blue squares around them. I'm going to allow this corner, this point on the avocado seed, to move around within the blue square to integer xy locations within the blue square. Any location there is a possible discrete label. I just have vectorize that set of labels, and every one of the blue squares is allowed to do its own search to find out where the point should be, so that our contour, our black contour, can hug the avocado seed. So we might come up with a unary cost which says that I like nodes that sit on the high gradient boundaries, or a nice high contrast edge between two colors. And we're going to make a pairwise term that says, oh, I like edges that are short, so I don't want any particular set of edges to be too long. I also don't want them to sit on top of each other, so I might have a penalty there. And in this way we could constrain the pairwise terms to say, I like W's, pairs of W's that are going to be tight fits around some kind of shape. So if we initialize, as we do here in figure A, and optimize for the variables that we've put blue squares around, we might end up with this configuration as we have in figure B. So this is the maximum a posteriori combination of W1, W2, and so on. Now, of course, we said that we actually have a chain, but we are actually supposed to be dealing with this as a loop. So now we're going to revisit this assumption of breaking the chain initially here, and instead we're going to reconnect the chain there. So now it's reconnected, and we're going to break the chain somewhere else and repeat the process. So we're going to solve for this again using dynamic programming, but our variables have changed. Now we might say this is W1, this is W2, and so on. And we optimize it, and after we've optimized it, we'll see that our contour is now starting to hug our avocado. And we could repeat this process by choosing to break the loop in other places, always solving for a chain, which we know we can do, and we know will give us, with the dynamic programming approach, will give us an optimal solution, at least for that slice of the problem. Okay, so conclusion, we know now how to set up our problems so that we can come up with the maximum a posteriori inferred solution where all the W's are consistent with each other as much as possible and with the unary costs underlying them, as long as we have a chain or a tree. We have a few tricks for changing grid models and models with loops into chains or trees, but for the next chapter we'll take on grids or loops, specifically using the GraphCut algorithm. Okay, thank you for watching.